Welcome, my friends. In this video, we will be introducing the most important distribution in statistics, and that is none other than the normal distribution. The normal distribution is so important as many variables naturally follow a normal distribution, such as weight, height, or blood pressure, and it is relied upon heavily in many inferential statistical methods, such as confidence intervals and hypothesis testing. This is what the graph of the normal distribution looks like. Let's discuss some of the important characteristics of the normal distribution. The normal distribution is symmetric about the mean mu, but being symmetric about the mean isn't enough to make a normal distribution. There are other distributions that are symmetric about their means, like the uniform distribution, which are not considered normal. The distribution also has to take on this shape, which we often call bell-shaped, because it looks sort of like a bell. The bell-shaped figure signifies that most of the observations fall close to the mean, and we observe fewer and fewer observations as we travel farther away from the mean, either in the positive or negative direction. The tails of the distribution approach but never reach the horizontal axis. This means that values in a normal distribution can take on any real number, although values get less and less likely as we travel further away from the mean. I should also note that the normal distribution is a continuous distribution, meaning we aren't restricted to any particular values, such as the whole numbers. Literally any real number is possible for a normal distribution. As with any continuous probability distribution, the area underneath the curve represents probability, and the total area is 1, or 100%. Now, not every normal distribution is exactly the same. The mean and standard deviation must be defined for any normal distribution, and can differ between normal distributions. In general, we use the notation x tilde n parentheses mu comma sigma to say that x follows a normal distribution with mean mu and standard deviation sigma. So this would mean that x follows a normal distribution with a mean of 100 and a standard deviation of 10. Changing the mean of a normal distribution just means shifting it left or right. For example, these three distributions are all normal distributions, except they have different means, -5, 0, and 5. A change in mean simply means shifting the distribution left or right. Changing the standard deviation, on the other hand, changes the shape of the distribution, making it either flatter or more narrow. Here are three normal distributions, each with a mean of 0, but now with different standard deviations. The blue curve has the smallest standard deviation of 1, making it more narrow. The red distribution has the largest standard deviation of 3, making it more flat, and the green distribution has a standard deviation of 1.5, and therefore falls somewhere in between the other two. One extremely important form of the normal distribution is what is called the standard normal distribution. The standard normal distribution has a mean of 0 and a standard deviation of 1. Typically, when someone refers to a z-distribution, they are referring to the standard normal distribution. A z-score, or standard score, represents the number of standard deviations an observation is away from the mean of that distribution, and is applied primarily to normal distributions. Finding a z-score is equivalent to converting values from any normal distribution into values of the standard normal distribution. If x represents an observed data point from a distribution, often called a raw score, mu represents the mean, and sigma represents the standard deviation, we can calculate a z-score by taking x minus mu divided by sigma. This calculation literally converts values from a normal distribution into the standard normal distribution, where each value represents the number of standard deviations the observation is away from the mean. For example, if we have a normal distribution with a mean of 100 and a standard deviation of 10, one of the possible values of that distribution is 90, which will be our x. The z-score for that observation is 90 minus 100 divided by 10, which is -10 divided by 10, or -1. This tells us that the z-score for 90 is -1, which represents one standard deviation below the mean. The observation 90 has been converted into a value on the standard normal distribution. Z-scores and the standard normal distribution are helpful for a number of different reasons. Here are two of those reasons. Mathematically, converting values from any normal distribution into the standard normal distribution makes it much more simple to calculate probabilities. The calculations still require integral calculus, which is beyond the scope of most introductory statistics courses, so we won't be covering the calculations here. Secondly, converting observations into z-scores makes comparing between different normal distributions much easier. To help you understand the second point, consider final exam scores from two different statistics classes. Final exam scores in the first section follow a normal distribution with a mean of 75 and a standard deviation of 5, and final exam scores in the second section follow a normal distribution, also with a mean of 75, but now the standard deviation is much bigger, at 10. For convenience, I've drawn the curves to look the same, although we know that the one with the larger standard deviation should be flatter. Which is a better score relative to the rest of the class? A score of 85 in the first section, or a score of 90 in the second section? To answer this question, we calculate a z-score for each observation. Z equals x minus mu divided by sigma. In the first class, this becomes 85 minus 75 divided by 5, which is 10 divided by 5, or 2. A score of 85 in the first section corresponds to a z-score of 2, which represents 2 standard deviations above the mean. In the second class, we have 90 minus 75 divided by 10, which is 15 divided by 10, or 1.5. A score of 90 in the second section corresponds to a z-score of 1.5, which represents 1.5 standard deviations above the mean. A score of 85 is more impressive in section 1 than a score of 90 in section 2, as it is more standard deviations above the mean. Just looking at the test scores, you probably would not come to that conclusion. A score of 90 seems to be better than a score of 85, and it very well might be for the final grade in the class, but in terms of comparing between the students, z-scores that represent standard deviations are the better way to go. We can also go backwards. If we know the z-score, we can calculate what is called the raw score. Remember that a z-score represents an observation expressed in the number of standard deviations from the mean. A raw score represents an observation expressed in the units of the problem, such as test score, weight, height, etc. The formula for a raw score x is based on the z-score formula and becomes x is equal to z times sigma plus mu. For example, if we took the final exam scores that followed a normal distribution with a mean of 75 and a standard deviation of 5, we might be asked to find the raw score that corresponds to a z-score of -2, or 2 standard deviations below the mean. Simply plug in z equals -2 into the formula. We have x is equal to -2 times 5 plus 75, which is -10 plus 75, or 65. A z-score of -2, which is 2 standard deviations below the mean, is associated with a final exam score of 65. Alright, my friends, that wraps up our introduction to the normal distribution.